rounds. 1, 2, 3, 4, 5, 6, 7. Yep. Breakfast. Okay, maybe I should reduce this offset a bit. What is the largest value that a row zero call ever takes? Ever becomes? Hey, it's a good question. If I know that, I mean, it's a fixed value, so might as well figure it out. Okay, the objective of offset is to make this positive. That's all. No, not, yeah, well, yeah, but it has to be a multiple of prime. Excuse-moi. I think I'm just going to calculate. I need some integer n that multiplied with prime is larger or equal to row zero call. Which means I need the ceiling of row zero call divided by prime. So we can do this plus prime minus 1 divided by prime. What wel? Static int. Is this correct? I think so. But I need to be able to print it at the end, so instead of a static I should use a global. Int versus prime type. This becomes a prime type, so well, whatever. Where's my global? It's not a prime. Let's use this. $17.67. Yeah, of course. I'll just remember that. So shall I write it down? 17. Excusez-moi. Is this in any way influenced by the size of the sieve word? It should not, but well, why not test it? Still 1767. Start it one more time with 8. I predict 1767. Yep. And I will leave it like that because it has no influence, and I'm going to use different compressions. Oh, that's rounded off exactly 10 times smaller. It's probably coincidence. It's probably more like a random generator. So again, exactly. No, it's not true. Five. One more. I'm not sure. I don't think I can do 2. Something went wrong. No, that doesn't work. Well, it's a far-fetched thing. I mean, it's not going to work at all. Where's my... I don't have it anymore. I wish you could remember this. The online encyclopedia, or yeah, it is. Who is? What is? Who is? 5,20,178,1767. Sorry, nobody knows what that was. Well, I do. Ha ha ha, evil laughter. I know a sequence nobody knows. I'm gonna use it as my save combination. Oh, I don't have a save. Yeah, for the sake of comments, I have to figure out why exactly that number, especially the largest number, because I'm curious. So what I really should do is let's calculate int 64 type and 2 is this one there, and then if n2 is larger than n, then n becomes n2, and I want to remember what goes with that, which is of course I think I have to remember prime. Oh, n prime. Oh no, it's prime. And what else do I want to remember? Call, I guess. I might as well remember this in row. That's everything that's involved here, right? Now I know prime and I know row, therefore we know n2. I'm not convinced, but in P and in R, doesn't get very static. Prime type in P, and the other was in R, which is a row, which is also prime type, I think. What's a row 0 content? Ints. NP and NR, now I have to print it. That's my prime. Yeah, I do interact with it, Jonas. I'm just not looking at it all the time. Why are you making prime number? Because I feel like it. Yeah, it's complicated. People have discouraged me to explain things. Sorry. Every time I explain things during my streams, and they just leave while I'm explaining, and I can't even see that people leave as no notification. So I'm not even, I don't know if you're still here, because I can't see that, which is ridiculous, and it's also playing a big role in not interacting that much with chat. I'll try to explain it, but say something so I know that you're still here. And P. Oh, that's great. If you will not leave, then I can spend a lot of time into explaining stuff. Then it's not wasted. You can leave, but please tell me in the chat. There was actually the row. If you just type row here, or 0 actually. Then. I'll explain in a minute, once I have these numbers. Pum, 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 pum. So I suppose I first have to explain to you then how this prime generator works, which is probably best done with a smaller compression than 6. So you know how the sieve of Eratosthenes works? You just have a big table, and each entry in the table represents an integer. And then you find the first prime, which is 2, and then you strike out every other bit in the sieve, in the array, eliminating all numbers that are divisible by 2. And then the smallest one that is left is 3. So then you strike out every other 3 number, and that makes you hit every number that is divisible by 6 as well, which was already struck out, because the divisible by 6 means it's divisible by 2. But you also get all the odd numbers that are divisible by 3. And so then the next number that is not divisible by 2 and not divisible by 3 is 5. So you strike out every other 5, and so on, right? But then you have a very large table with all the integers. So in this case, we generate all primes below 1 billion. So you would need 1 billion bits to represent every integer, and it's kind of silly. Nobody does that. At the very least, you just allocate the half of that. You eliminate all even numbers from the start. So now every next bit is exactly an offset of 2 further. The first one stands for 3, and then the next bit is 5, the next bit is 7, the next bit is 9. And then you start with striking out every third bit, which then means that you start with the 3. Now, compressed means that you go even further, and compression of 6 means we skip the first 6 primes. So I'm having a table where each bit represents an integer that is not divisible by 2, not divisible by 3, not divisible by 5, not divisible by 7, not divisible by 11, and not divisible by 13. Now I'm Dutch. And that starts to repeat after 5,760 entries. And we can make a table, so we list all those integers that are not divisible by 2, 3, 5, 11, and 13 in a 2D table of 5,760 wide, and as long as it needs to be. That is a bit large, so instead let's look at the smaller compression. Just all the numbers that are not divisible by 2, 3 and 5. And I need a comment. Beats me. No, that didn't work. How about this one? Yeah. So here's a representation of that table where we start with 7, because that's the first number that's not divisible by 2 and not by 3 and not by 5. And now you see that if we just list every number, then of course the first number that's not a prime is going to be 49, which is 7 times 7. Every smaller number is either a prime or is divisible by 2, 3 or 5. So these are not primes, they're just not divisible by 2, 3 and 5. Any larger number will occur. Like 11 times 13 will occur in this table. Whoops. 7 times 19 will occur in this table, and so on. Just pick any number times any other number times any other number if you want to, and it will occur in this table. But the funny thing is now that if we make this table 8 wide, then, and not by coincidence, every number a row lower is exactly 30 larger, where 30 is 2 times 3 times 5, not by coincidence. So this is plus 30, plus 30, plus 30, plus 30, and so on. And also here, 11 plus 30 is 41, plus 30, and so on. Every column is going down is just, you know, this is repeated. So the offset repeats. So this is plus 4, and then plus 2, plus 4, plus 2, plus 4, plus 6, plus 2, and then from here to there's plus 6. And then we repeat. So this again is plus 4, just like from 7 to 11. And then again plus 2, just like from 11 to 13. So logically, going all the way here, and then from 61 to 67 is again plus 6. We have again added 30. Yeah, because the offsets repeat. And that's the same from any number. So if you go here and you repeat that exact stuff, then you just add all those offsets added together is just equal to 30. Now we are going to do the following. At some point I need to calculate, well, let's say I have this, each entry here is represented by a single bit in the sieve. And we find, let's say, the 17 is the next prime. Yeah, we already found 7, 11, 13, now we find 17. Then we have to strike out, so reset the bit in the table that represents all the numbers that are divisible by 17. Now that is of course 17, but also 187, and also 221, and also 473. That seems pretty random, right? However, in the same column, the distance is the same. For example, 119 is divisible by 17. I see that because the dollar here marks all the numbers that are divisible by 17. So I see a dollar here. 119 is divisible by 17. And so is, let me find the next dollar, so is 629. And this distance, vertically, so the number of rows here, is equal to, well, hold on to your seat, 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And the next one is going to be 17 down again. Why? because the difference between each number is 30, which is 2 times 3 times 5, which is always not divisible by any prime we're going to find. Larger than, you always start with 5, so it's not divisible by 17. So you have to add, if you have a number that's divisible by 17 and you add 30, which is a co-prime with 17, you just have to add that 17 times before you get the next one. So we strike out this one, and then we add 17 rows, and we strike out that one, and so on. And that's the same in every column, right? So if you find this one, that's the first one. That's divisible by 17. Then 17 down is the next one, and so on. So now the problem is reduced. The problem of resetting every bit in the whole table, in the whole sieve, that is divisible by some prime, for example 17, is by doing this in every column for that prime, and then finding the first number in that column that is divisible by that prime. And we can do that as follows. I have a comment about that as well somewhere. Let me see if we can find that. Yeah, here. Now, for example, column 2, which has 13 in it, and then plus 30, plus 30, plus 30, plus 30. Yeah? So this is column 2. This is the row. And now we want to find the first number that is divisible by 19. So not 17, but 19. Now I write down here the modulo 19 of this column. Then, well, you know what modulo is, I hope. So this is 13, and then this is the rest value after the remainder after dividing by 19. So this is like 2 times 19 plus 5 is 43. We get 13, 5, 16, 8, and 0. 0, if you have a remainder of 0 after dividing by 19, then of course it's the number divisible by 19. So this is the first number that is divisible by 19, because it's the first number that has a modulo of 0. Modulo 19 is the first number that is equals 0, modulo 19. Yep, the remainder or the rest. Now note that 133 can be written as 13 plus the row times 30. Yeah, because vertically we just add 30 every time, and we start with 13. So the row is 4, we start with 13, 133 must be equal to 13 plus 4 times 30, okay? And we want that to be equal to 0 modulo 19. So we're going to do modular arithmetic. You can solve this for 4. In order for this to be true, the 4 times 30 must be equal to a minus 13. Just subtract 13 from both sides. Modulo 19, right? From which you can solve the 4. 4 must be equal to a minus 13 divided by 30. Mod 19. Since 19 is a prime, it's always a prime, you're having a field. So everything, addition, subtraction, multiplication, division is defined. So you can just do this in a modular field Z19. It does, however, require a special code that allows us to do a modular division. We must be able to divide by that. Now, C++ supports modulo with the percentage, but not modular division. You can do easily addition or subtraction, even multiplication actually. You just do that in the normal Z, so all the integers, and then you do the modulo. But for division that doesn't work. So we have to add special code that allows us to do a modular division, which is here at the top. This is modular. This does modular division. That's the extended Euler algorithm that's also used to calculate the greatest common divisor. But extended means that you add another pair of variables, which then returns the inverse of the number that you passed, modulo m. So the return here is the inverse of n modulo m. That's a very fast algorithm as well. And now the problem is that I ask myself, when does that overflow? When does it get too large? So I had this, see, this comment here describes that. I define P is the compression primordial, so that's the 30. F is the compression first prime, that's the 7 in our case. And then the first prime of the second row is thus the first prime in the first row plus that, sorry, the other way around. The first prime in the first row plus the primordial, so that would be 7 plus 30 is 37, which you can see, I guess, here in the table. Obviously, it's just 7 plus 30, so this is the first prime in the, or the first number anyway, in the first column. And then I do a guess, a wild guess, more ballpark guess for how large those numbers are going to get while I'm doing my calculations. And the conclusion is that P plus F to the power 3 must still fit in an integer. I told myself discrete math, actually, just using internet. So 1290 to the power 3, that's the largest number that we're going to run into, more or less. I mean, it's larger than what you're actually going to run into, but yeah, good enough. This to the power 3 is the largest thing that fits into an int. So this may not be larger than that, and therefore, and these are the actual values, which means that if you have a compression of 5 or 6, then it would overflow unless I do an extra modulo at the right moment. So this line here. If const expression, this is a const expression, this is a constant, of course. So during compile time, this can be evaluated. And then if const expression means that during compile time, it's decided if this is going to be compiled or not. So if this is larger, then I insert an extra modulo here, otherwise we get an overflow. Well, it's faster because the small primes take most time. Plus, you have a large amount of memory. You have a large sieve, right? So if you have a larger amount of memory, and you have to make small steps. Small primes means you have to strike out a lot of bits. So we start with 17 as the smallest prime instead of, well, let's say 3, if you skip the 2 anyway. Then we'll already stepping 17 divided by 3 is 5.666 times faster, plus the table is smaller. So it's just going way, way faster. Larger steps, smaller sieve. That is so much faster that we can spend some time on calculating that modular inverse and still gain time. Now, yeah, anyway, I had to explain all that because you asked. What do you ask? You ask, what are you doing? You said, I don't understand what you're trying to test. In the meantime, I forgot what I was doing. Oh yeah, it was this here. All this, I mean, I just don't like this extra modulo, okay? I mean, maybe I had a different reason I forgot. But if I want to get rid of this, which is just, you know, it's no matter how you look at it, it would be faster if I can remove this this modulo here. Then I want to get rid of my overflow. And I would get rid of my overflow if I just use a much smaller offset value. So it's trying to see if the offset that I'm using, which is currently compression first prime second row times prime, which is about 30,037, I think. While in fact, it turns out I can use just 1767. So we can do that exactly then. 30,037 divided by 1767. That's almost 17 times smaller. And that might at least remove the modulo for the compression 5. Just have to check that yet. I think we got safely use compression 6. I mean, if I use less than that, it's definitely all going to be smaller. So we can make it work for the compression 6 or maybe 5 then. I don't have to look at the smaller values, it's just going to work. Yeah, I wanted to understand where this 1767 comes from. So I'm going to remember these two values at the moment we find it, print them out, and then think about that. See if we can understand why I already have them here. Prime is 17 and the row is that. No, well, that's just the largest row value. Why does prime 17? I don't know. This is the last. No, actually, there's one more larger, but okay. It's almost the largest value in row 0, so all the way to the right, is 30,031. So this is the second largest value, which is, I guess, logical. The larger the row value that we subtract, the larger the offset has to be. And I require that number to be the largest number together with prime 17 for some reason. Well, 17 times 1767 is 30,039, so that is larger than that. You can ask yourself, why not 13? Well, apparently, the larger this prime, the more overshoot you might have, or it's just a coincidence, I guess. But it can't really be a coincidence that it is such a small number. Of course, This times that must be just larger than that number, or equal. And now you demand that this is a maximum value. Well, obviously, that then has to be very large, like the last or the second last number, which is the largest, as large as possible. And the prime has got to be small, because if the prime was like 10 times larger, then this number can be 10 times smaller. So the prime tends to be small as possible in order to force that one to be large. But on the other hand, it tends to be large because you want to overshoot that number. And you take increments. Every time I add one here, you add that prime, right? For the vector, for the multiplication here. So if the prime would be 5, say, then then you overshoot it not as much. I think. Well, no, there is no 5. Let me think. No, I don't get it, actually. I would say that this number must be larger or a smaller prime. Oh, yeah, I'm an idiot. This is the first prime. It is the smallest prime. The compression 6 means we skip the first 6 primes. So we skip 2, 3, 5, 7, 11, and 13. So 17 is the smallest prime. So this as small as possible, that as large as possible. That's logical. However, there is one value that is larger, and then you can ask yourself, why didn't we take that one? And then the answer is 30031, I think was the last one, divided by 17. I think that's also 1767. 1767 times 17. Yes, of course. That's already larger than the largest one. So maybe it's more like we only replace this when it's actually larger. So we don't replace it when it's equal. What if we do? So oh, that doesn't work. It's an arrow. Make yeah, so now we have the smallest prime and the largest row value. How logical. I could have thought that. Could have thought it myself. Unbelievable. Yeah, okay. Well. Okay, let's do that. But The question is, do I get rid of my overflow now or not? Do I have to do that whole calculation again or not? That is a bit too much, this. We might as well use Gotta be kidding me, right? Getting the same number. Oh, wait a minute. No, we're not. The times prime is there. Yeah. Okay. So it's compression first prime smaller. That's 17 times smaller then. Theoretically, I would use let me see, I think I can use row 0 here. I'm gonna do last prime row 0 or something like that. So the last prime row 0 divided by the first prime and then round it up. So I have to add that first prime, subtract 1, divided by that. So this is 30,031. And this is 17, so plus 16 is that. Divided by 17 is that. And then rounded down, that is 1767 as expected. And that we use then as the multiplier for the current prime. So depending on the compression, I'll put the compression in front of it as prefix. Call this the offset multiplier times prime. So I need to define that. And I first need to calculate the row, which is a const expression, so I should be able to put it there. Compression offset multiplier is then equal to that. And then the compression last prime row 0 is equal to row 0. Yeah, dot back. It should still be a const expression. Right. Well, that's enough. So how is that influencing my FP story? Wherever that was. Yeah. The largest value of offset minus row 0 call is when offset has its largest value and a row call is at its smallest. The latter happens when call equals 0. at which point rho 0 call equals compression first prime. The former offset is at its larger when prime is at its largest, which is compression first prime second row. Note that compression first prime second row equals compression first prime plus compression primordial. Let P is compression primordial and F is compression first prime. Then compression first prime second row is P plus F. And we can write for the largest values involved, prime equals F plus P plus F. Is that correct? The prime is at its largest when a prime is at its largest, which is at the first prime of the second row, which is equal to the first prime plus the primordial. So that's still this indeed. And minus rho 0 call is minus the first prime. And the offset now changed. The offset is now a different factor. Different factor times prime. So prime being P plus F. Yeah, I'm just going to fill it in, I think. Or shall I use the formula? Nah. Actually, it was 0.30 divided by the primordial divided by 17. Close enough. Oops. It is more or less P divided by F. Yeah. Let's use a slightly larger value or not? That's actually correct, yeah. Let's do P plus F divided by F. It's not exactly. It's more or less. It happens to be exact after round off for compression 6. So P primordial is primordial. Again, you notice a conjunction of the thing of factorial and prime. So it's 2 times 3 times 5 times 7 times 11 times 13 is 30,030. And the first prime is, so the next prime after 13 is 17. So we have here 17 plus 30030. divided by 17, and that is 1767, as it should be. We have to round it down then. It is 0.470 and stuff, but well, it's just a ballpark calculation anyway. So that is what I had before, but divided by f. That's 17 times smaller. What I saw in my previous calculations, it's 16.99 smaller. But yeah, okay. So the largest possible value of compression primordial inverse is prime minus 1 or p plus f minus 1. Yeah, this was very inaccurate. Of course, there is always going to be a number that has exactly prime minus 1 as inverse, modular prime. But then to assume that plays exactly the role at the moment that offset must be at its maximum. I don't know. Let's do it anyway. Let's see what happens. Thus, the largest possible value of offset minus rho 0 call. And I have to divide this by f. Division, horrible. It was such a nice polynomial. Now I have to divide by f. I have a good idea. We don't do this. Back then I thought maybe it will tell me something, but it doesn't tell me anything. I'm just going to fill this in exactly. Offset minus f times compression primordial inverse, maximum value. Oops. So if we skip the first two primes, that's 2 and 3, then the first prime that we don't skip is 5, and so on. P is the primordial, so that is 2 times 3, I think. No. I'm lazy. Just going to look at my table. Yeah, the first prime is 7, then the primordial is 30. So this one is 30. 30 is just 2 times 3 times 5. Yeah, so it's just the first 3 primes. So then this one is 6, 2 times 3. And then 6 times 5, so this one must be multiplied by 7. 210. 210 times 11. 2310. And times 17. It's 3970. Why do I not recognize that number? Because it had to be done times 13. That's much better. Right, and then I want to calculate m as being that formula. I'm lazy, so no. Is it doing actually? It's doing it wrong. 10, yeah, it's doing it wrong. Stop generating. Yes. P plus f divided by f. P plus f divided by f, and then the floor times P plus f minus f, and then all times P plus f minus 1. Yeah. Since when is it doing calculations by itself instead of relying on alpha 0? Alpha 0. Wolfram alpha. 5, 6, 7, 30, 11, 2, 10. That's bullshit. Oh no, wait a minute, it's not bullshit. I'm looking wrong. No, for some reason it's doing calculations correctly. Shall we believe it? Well, let's test the last one. I want to test the last one myself from scratch. 30030 plus 17 is that, divided by 17 is, I already knew that number. 1767 times 30047. It's not what I got. Did I make a mistake? Man, this is costing more time than when I would have done this myself from the start. This is wrong, isn't it? 1767 times 30047. Yeah, this number's wrong. Whoops. I'm going to be stubborn and say Jonas says, let me reduce. Just generate the primes themselves, put them all in the vector. And in my program, I just have this list hard-coded in. Still not convinced. Damn it. I mean, it doesn't really matter. I just want a ballpark figure, but I cannot put this in my comments, and that is wrong. So I just have to. Just have to write a little program. I think I don't believe this number. I mean, now I use Wolfram and stuff, so maybe I'm mistaken, but yeah. I guess I'm mistaken, because Wolfram says that it is this number, then it should be that number. Let's just verify this one. If this one's correct, then I'll believe that one as well. So again, we have 1767 times 30030 plus 17 minus 17 times no, it is correct. Okay, let's copy this. Where's my comment? I think this is still larger, right? Does not fit in an int, this one. What? Still incredibly much bigger. At least this fits in an int. Yeah, I want to use a compression of 6 anyway. So it didn't really help then. Can I not calculate the 64 bits instead? Probably. Remove the other ones. Still faster. Even this one. No, it's still faster. Oh well. I did my best. But all of this is working with just this one fucking thing. So why would I not make this an unsigned int 64-bit? Aha, 1.35. So it did matter. We didn't get as much gain as we could have. Ah, yes. I love this. What am I doing? I'm not sure I want extra pedantic, but let's see what happens. Oh, it's signed. As usual. Interesting. What? Oh, I'm no longer using it, except for the assert, but well. Even that doesn't seem very correct then. Why is this so quiet? Oh, right. Yeah, well, okay. Okay, so then we want to have that one only when debugging. Oh, that's debug. Non-standard my ass. So I do not want a pedantic then. What is it doing here? What is there? Different sign. That's the wrong thing. Yeah. Or not. Let's just cast the unsigned to whatever sign type we have. PI. This is an int. Okay, the next row 1. Probably have to start the same. Not sure though. Right. Yeah, I could have a loop over the inner loop is the most important one, right? So this is probably the most important one. Definitely want to have a loop over a column mask. And then we need a word index ready to do this check. Okay, so insert that. And that's the same check. I want the same check. Hi Jay. Sam, I don't know what you're asking. You see what I do? I have if statements, yes, and for loops. So I just inserted these 4 lines, right? because I want it to work. I'm going to need a word index, and we do need a row and a column. I have my row and column already ready here. So this is a matter of emptying your mind and then waiting until the thought comes out. What the fuck you have to do next? I think I'm just getting old. Yeah, column is maintained here already. Every time column is 0, and then the next time we go to the next column mask, and obviously we have the next column as well. I need my word index. I think word index should be equal to words per row. That was already the case. I could reuse the same variable, but it doesn't really matter. Compiler will do that, so we could just make a new word index in my loop and then set it to words per row. So we get something like that, something like it, instead of this loop. That should start at word index per row, because we started row 1. And in this case we continue forever. So now I have my word index, but I'm not maintaining a row yet. So maybe I should keep this actually in it. Or like a word index offset. The word is, yeah, it's a word index offset. Did I already use that? I have a column word offset here. I like word index offset more, but I think that's the same thing. Yeah, totally is. Let's see what this is being used. %. That's the next loop, I think. %, yeah. So it's only being used here, and I don't need it anymore, or don't want it anymore, or just delete it. That was the whole point. You want to get rid of everything here. And that's, well, clean up. So now every time we start the word offset, that is now the word offset, or the index offset, whatever, relative to the start of the row. So every time we start again at 0, then we increment the row. So it can do the same thing here, plus row. And then we maintain the row as well. However, this means that we need another loop, because now we don't start at all. Wait, it's nonsense. No, nonsense. I mean, actually here, row something plus row. I'm already having a next row here. Column is 0. Column is 0. Well, yes, that's what you would expect if you start a new row. So all code should be inside this loop. That is to catch the break, I guess. No. Do we have a break? We have a break. This break. I think I need 3, 4 loops. So this one loops over the column mask inside a word. And then this one loops over all the words inside a row. So we get out of this loop, then we enter the new row. So plus plus row, column is equals 0 again. Then we go to this top here, so we might as well move that to here, and I don't need that anymore. And a plus plus row we also already have at the end here, or I can just not do it and put it here. I don't know. Why not? This now suspiciously looks like a do-while loop. Maybe we should make a do-while loop. Suppose row 1 doesn't even exist. What happens? I guess we would just calculate the new prime and then see that it is larger than the square root. And then break. And that should leave everything. I don't care about the row anymore then, or do I? I probably do. A row should probably stay at 1 in that case. So yeah, it's the same thing, right? So I'm gonna make this a do loop, do while. And that's only because, well, we always enter here, we always enter here, and we assume that we find a prime. What if we never find a prime? Not in time anyway. Then prime is not defined. Yeah, we are, of course we're going to find a prime. But are we? It's not entirely certain, is it? So, theoretically you could never find a prime in the whole word, in the whole row. Leave here and then prime is undefined, or prime is still equal to the previous prime, which means that it's definitely less than that, so we are going to go back to the top. But for the next row, okay, why not? Yeah, it looks good. So I need a plus plus row here, that's for sure. Still need my word index. I think the word index was an int. The word index should be bullshit. Let's use a sieve. Let's use a row pointer instead of sieve. Point to the start of the row. Uh-oh, save word index. This is a different word index, so that should work. Okay. Now I need a word index. I mean a row pointer. So that's a sieve word type pointer. Which gets added words per row. Every time. I'm just going to initialize it here, I think. Might well do the add here or not. Yeah, let's do the add there. So we set it to equal to sieve here. We start with an addition, so we skip the first row, so row 0. So the first time we go to row 1 by adding that. Something is so wrong here. Of course, it must be done per row. Okay, so points to the beginning or start? Start of a row? No, start of the row. Loop over all rows, starting with row 1. Update row pointer to point to the start of the current row. Then maybe I can delete this. Well, that speaks for itself. If you start a new row, then the column is 0. Now, suppose we break here. Now we are in the middle of 3 loops, and I want to break out of all loops. This is one of the most annoying things I can imagine. That if you can only break out 1 loop. So really, seriously, no way to break out of 3 loops. Go to, where are you when you need me? Well, actually, maybe go to just works, right? I mean, let's try go to. Done. Better than a break. And now we don't even need this, I think. If it works. Let me first test if it compiles. Test if this compiles. Word index offsets. Yeah, it compiles. And now I think about it, it should also work. Would be nice, you know. It worked. Are you amazed? Anyone amazed? Tell me in the chat. Jay says hi. Hi, Jay. How can I ask, how can I learn to code and level you are on? Is Jay still in the chat? Because, you know, I don't see anyone in the chat. Will you believe that? Just YouTube sucks. Ed. Nope. Seems nobody's in the chat. Still there. Yeah, well, I didn't see it for 14 minutes, so I can't really blame him that he lied. Row pointer, word index offsets. Yeah, what do I see? No, I don't know anymore what I was doing. All that. Make. Oh, it worked. Yeah, really, I've completely forgot what I was doing. It worked. And then, what was I going to do? Well, this. Apparently that works, so I don't need other tests if I have those. Mostly that one. So this becomes a for loop now. Endless for loop. Oh, you're still there. Sorry. I blame YouTube. I look at participants in the chat and then they already removed you. Well, then I have to give you an answer. Right? So you say, how can I learn to code on the level you are on? I don't know my level. So, yeah. I think the answer is complicated. Because I'm probably a lot worse than I should be, if you get what I mean. So let's say if you do fighting sports, karate or something like that, then at some point you develop reflexes, right? You don't have to think about it anymore. You just, someone tries to hit you and hop, there goes your arm automatically to swipe the hit away and take over. And you get that by repetition, a lot of repetition. So practice. And then once it is a complete automatism, then you are not aware of it anymore. The only thing I can tell you is I started coding when I was 12, and I've done it a lot. And a large part of my life, by far the largest part of my life. In the beginning I did school and university, of course. And then around 30 years old, I didn't do anything anymore than code. And now I'm 59. So I have coded like my whole life, 7 days a week, non-stop, more or less. Plus, I have a talent for it a little bit because, I don't know, at least I've been tested to have a very high IQ. And I have a form of autism, which makes me, very concentrated on just one thing, which is coding. So if you add that all up, then yes, please let me be good at one thing. But then you ask, how do I get to that level? I'm not even sure that if you want it. I mean, I don't think I'm that good. So let me make that clear. But since I'm not stupid and I have not done anything else my whole life, I should be at a level that is, I don't know, up there. That's certainly for certain things. So if you look at, say, the world champion chess, or the top grandmasters of the world in chess, and you ask, how can I get that good? Then I think the first question you should have is, do I even want that? Because all those top grandmasters, they do not do anything else. They started in their childhood playing chess, and that's the only thing they did. And now that's the only thing they know. And that's the only way to become at the top. Now I don't know if I'm at any top, but I sure as hell have devoted my life doing nothing else but coding. So I think it's just not how it works. You don't set this as a goal. It's the other way around. You are, I don't know, socially awkward and autistic, and you like computers and you code all day. And then as a side effect, you get good at it at some point. But you should not, and you are not going to devote your life to one thing because you want to become good. That's not how it works. And I did chase away 6 viewers. No, it's not true. I had 6 viewers by that time. I saw a peak viewers of 10. Normally I discover that. So whoop, window run. Now I don't see anymore how many viewers I have. Much better. How did you learn to code? I just taught myself from a book. So my dad was a programmer, or actually a system analyst. And he did a Telia course over the television in 1976. So he got books. It was just A4 printed stuff in a binder, to do the course. And, I read the book and then I could program. And then I wrote my program, my first program on paper, which was prime generator, yes. And then he was going to buy a die. The PCs didn't exist yet. Let's see if we can find a picture of a die. Yeah, I bought this one. So he bought this thing at some point. 1980? No fucking way. That was later. I wrote my first program for... Yeah, I started on TRS-80. So 1980, I was 16 then? Then I was older. Well, I started at 12 on the TRS-80. Find it. Let's see if we can find that. TRS-80. That was in a shop. Somewhere in the city I found a shop where you just could walk in and start coding. Very nice of these people. This machine. Oh yeah, that gives certain vibes. Seeing that again. I was addicted from the very start. Coding, writing programs. I'm going back to real coding. Anyway, all those questions, dude, in short, just begin. Just start. Open a terminal and type in whatever comes to mind and what interests you. And that way you will learn automatically. Yeah, I have a Discord that I never look at. So if you say something there, then I would guess that maybe I see it then within a week or so. Because let me try to find Discord back. It's completely buried. That's my Discord server. "25 people are online right now and nobody's talking there. Quite a few people actually. More than 100. And nobody's talking. Yeah, someone asked me something here. Can you look at... Yeah, no, I cannot. I already talked about that, I think, on the stream. Okay, let's continue here. I think this is now done, right? And then we have a prime. Yeah, this test that costs an annoying amount of CPU cycles. So really no way that you can know in advance when to stop. Or maybe guess a neighborhood where to stop and then track back. So I don't have to test every prime if it is already larger than that. Or is that peanuts? Is that really not important? Should not be important. I guess this is a register. It costs a register more or less. And probably going to read it from memory, but then it's from cache, so it shouldn't be slow. Yeah. My God, I'm struggling to get normal music here. I mean, music without singing. No idea how much time I would gain to remove this. So you would be able to guess when you can stop, but you have to overshoot maybe, or maybe if I undershoot. So we could create yet another loop. So we just do a lot of primes, and then when you get near this value, we start yet another loop, which then does have the check in it. And then I could test, say, a row until a certain row. Actually, I can do that. Of course I can do that. It's even easy to calculate. Yeah, I just don't know if I want to do here even more code. I mean, loading extra. If you add extra code, then that code has to be read from ROM. So then we win a few microseconds by removing this, and then it has to load more executable code to continue the last part, and that's going to take a long time reading the new executable. Or maybe it preloads it, I don't know. Because, well, it knows that it's going to advance here. It's maybe a bit too fancy. But on the other hand, it is damn easy to know which row has to be done completely. That would be just simply the row that has at the end a number that is smaller than this number. And we know what is at the end. That's the last prime plus the compression primordial times the row. Oh, it's a single division or something like that. To find out what is the last row that we can do without checking this. But yeah, it isn't even the inner loop. So 2 more loops after that. So probably doesn't gain much or at all. And like I said, then I have to do a lot of code duplication. Or function calls maybe. Oh no, you want to get rid of this line, then I think I'm going to leave it in. This one also here. Do we gain anything by the extra code modular inverse 2? That's a different function that just assumes that this is true. And therefore it's a little bit faster, but it's a different function. More code to load. So what happens if I do not call that? Let me try. To time that. Home time. We are at the square root of 2 seconds. Okay. It varies a little bit. That's a very small one, almost 1.4 seconds. And now I'm going to change this into just use the same function as above. Well, that seems to make no difference, right? Oh, it's even smaller than what I had just as. Okay, so that function doesn't take any time. I'm not going to have a different function for that. It's just stupid. It doesn't even look good. How can this work? One of these things 64-bit. Oh, prime is 64-bit. That's why it works. So this is 64 bits, and then mine is 32 bits, but it's still 64 bits, and then times 32 bits, but it's still 64 bits, and then in modulo, and then it fits into 32-bit again. All by coincidence, as it were. And then call word offset. Call, yeah, I don't like that at all. Another heavy division. Can get rid of these two. I think this code is from this point on, or maybe I think it's the same as the one above this. So after we calculated that, So I want to have this loop. To have this loop. That's just the same thing, right? In sieve. Should be the same, but that's the same as I had. And then we use VI instead of word index, but why not? So this is not even changing then, but okay. And then above that, calculation is different, but I have that. And it uses a call. Which we then make from this. So I have a word step and a compression primordial inverse and no offset. Word step, compression primordial inverse, no offset. And now we do these loops, 5 more lines. And then I have my call, which is incremented here, and then I have a call word offset and a call mask. So we have call word offset and call mask. And that is then gone. This must be shifted. We have an extra loop. Okay, call is 0. Yeah, that's a next loop. So this is till the square root of Maxwell. All starting with row 1 up till and including. No, not including. Wait a minute. Yeah, well, including. For all rows starting at row 1. And we have less than 1.4 seconds. Oh, wait a minute. Well, it still was the case. And now we have almost 1.5 seconds. It's still 1.4. For a second I thought it was faster, but no. Doesn't look like it at all now. Okay. Still, I guess that loop is now done. This loop is done. Oh. What the hell, man? Before we had 1.41 continuously. It got slower. So only sometimes. Yeah, no, this is low, but I want to do some benchmarking, I think, because I'm interested in know which part of the code is using a lot of cha. Oh, yeah, whatever. Commit. Hello, Matthias. I'm gonna do some benchmarks. I have that in my library. Benchmark. Let's see how that worked again. Yeah, this is more for measuring a single instruction. It's like clock cycles. But then you have to repeat the same code a lot of times. This is executed a few times. You don't want that. I'm just going to abuse the stopwatch, I think. Stopwatch is also pretty damn accurate. So then I still have to include benchmark. Then we get the stopwatch. let's begin with that. I need to include this. See if that works. Oh my god, utils. Oh well. I guess we have to add utils then. Repositories. Utils. Utils. The rest is already set up. Not sure configure is enough in this case. I might have to run autogen on this sh. Pretty much. Well, it compiles. And then I can do, well, we have to initialize it. I was looking at the file words. VI, this one. Example code. Need a loop size and a minimum of. I'm not sure that the calibration is probably for the loop, for the measure. I'm not even sure. Stopwatch, it sets S stopwatch overhead, I think. The value of 0 means uninitialized. It's impossible to overhead a 0. And I could use that. Or is it already used somewhere? And if so, where? Calibrate overhead, you set it to something. The overhead of calling start stop in clock cycles, yeah. So that's useful. But it's only used in measure. But okay, you can use it anyway. Subtract ourselves from the number of clock cycles that I get. let's just do that as well. Everything. Copy. Sort of. I don't think I need 10K. Okay, what's my CPU frequency for this thing? Okay, let's see. And proc CPU info maybe. CPU megahertz. That's considerably lower than what I just thought. This is better. Whoa, it even goes up till 4. Because it's cores that are not used run at 2.2. So we have no idea what it is. I'm gonna assume that it runs at 4 gigahertz, more or less. Man, that's inaccurate. Yeah, you have to change something in the BIOS, I think, to make the clock stable, which I'm totally not going to do. So that's good enough for me. This value, some value, whatever. Well, the number of clock cycles are correct anyway. It's just calculating back from clock cycles to the time that it takes. And that's just relative, so I don't really care. Now let's add some code that does an actual calculation. Because now I have a stopwatch here, but I need my stopwatch elsewhere. Don't tell me I have to pass the stopwatch to the other function, calibrate overhead. Can make a new stopwatch, I think, in calculate primes. Don't want to pass it. CPU. Should be the current CPU. Because that's automatically done. I don't know. Would be a bit weird if it didn't. See what happens here. CPU NR. I think I should use CPU NE then. That's whatever it's running on. Stopwatch CPU NE. Okay, so we call start and stop. And then diff cycles is the number of cycles that it took. I suppose. Mm-hmm. God, again, what it was? Something with overhead. Stopwatch overhead. And then, yeah, cycles is a bit too on the vague for me, so we're going to divide it by CPU frequency. It's apparently a double. Let's use that. It's a big function. So that would be in seconds then. benchmark stopwatch. I kind of have to or want to do this with optimization on, right? So why is it using debug here? Okay, so this is release mode. We don't have that. So that should return 0 cycles. Well, at least here 0 cycles, because there's absolutely nothing being done in between. Well, that is a precision of 10 nanoseconds. In terms of the 0. Hello, Icon. I'm just calculating prime numbers. Yay. Hey, Pice Bunny. Yeah, this is nonsense thus, because what shall I measure here? Let's measure let's measure this one. Allocating. It's definitely a thing to measure. So allocating, how long does allocating the vector take? Time spent allocating the vector, the result vector. Let's try to do it again for start, stop. Time spent writing the first compression primes. Now that's pretty well, reasonable. 40 milliseconds just to allocate a vector. I mean, it's, if you compare that, as those, it's just a pretty reasonable small fraction. It's 4% of the whole time. Less than 3% the whole time. I don't know. But again, 33 milliseconds. 34 milliseconds. And this is 10 nanoseconds, so the writing primes is completely neglectable. Don't even want to measure that anymore. Let's measure the next thing. I don't think this is going to take much. Oh, allocating the sieve. Allocating the sieve and setting it, filling it with all ones. That should definitely be measurable. I should remove this because it doesn't work. Let's just remove it. Oops. Oops. Undo. So the next thing. Time spent allocating sieve. Allocating and initializing sieve. Unused variable partial mask. Yeah, that's no longer used. That's pretty amazing. Only 2.5 milliseconds for the allocation of the sieve and filling it. Well, this also fills it with zeros, I think. So, well, it's comparable, and it's more than 10 times slow. So, if you should not really. I mean, yeah, well, you have to write the result, but if creating the result vector and writing the primes is going to take most of the time, then the sieve is pretty damn fast. So I am happy with the 2.5 milliseconds for the setting up the whole sieve. Okay, so let's copy this. And then measure the next thing. Because row 0 is it's going to be pretty considerable, I think. Time spent sieving. What is it? Sifting. Row 0. That's so going to be a lot of time, I think. Might as well add the rest. Time spent sieving row 1 till row. What? Row 1 till 1? Oh, really? So there is almost nothing, well, nothing. There is literally nothing to do past row 0. That's ridiculous. Let me reduce the compression a bit, see what happens then. Oh, that's true actually. Yeah, this should be more evenly. Now we have to do 13 rows. So pretty much fast. You the smallest primes are really slowest. Definitely by far the slowest. Reproducible. Reasonable, reproducible. Yeah, well, what you want to say about it? And it total comes slower. Interesting. Row 0 is hardly slower. How the F is that possible, man? The next compression has a row that's 13 times longer. Yet it is almost as fast. What? I gotta wonder, can I do larger things already? 1 0 extra. Oh my god. How is that possible? I do 10 times more integers and it gets more than 10 slower. What? That should not have happened. Is it even correct? Not convinced that it is correct. Oh no, that is not correct then. This is the prime. It is, oh, it did overshoot. So, and that's complete nonsense. So this is what it should be. I think I had an overflow somewhere. Way too small. This doesn't fit in an int. Is that the problem? Fuck. No fun. And already 22 seconds. I'm gonna do a 0 more. So that's gonna take several minutes. I'm sorry for that, but I want to see what happens. It's time to eat. Well, I'm using a lot of memory now. Actually, I'm using half of my swap. Why? I've added another 0, which was my objective. I would need 24 gigabytes, I think, of sieve. Yeah, if you see that this one is already 16 times larger, or takes longer. I guess I'm storing 8 bytes per. Oh yes, that's the reason. This the vector itself is way larger. No, it's not true. There are not that many primes. Well, this just takes a long time. So I want to know the. I want to know all the primes below this number, 10 to the power 12. Whoa, it can do the, whatever this number is, prime. This side. It's even 30 times larger than that. Holy moly. We want to go to this. Oh, it's still big. Way bigger than I expected. Okay, I want to have The number of primes below. So that is this one. I think that is this. Yeah, big. I don't have that not that much memory. So if I wanted to do all primes below this number, so there are this many primes. I need 1 bit per prime now for the sieve, so that would be 37 divided by 8 bytes, gigabytes. 37.6 divided by 8, so less than I thought. 4.7 gigabyte. I have that. But I can't store the primes because each prime, I saw each prime in 64-bit thing. No, I stored it in ints actually. Which also wouldn't fit anymore now I think about it. But that's, I think it's done actually. 4 minutes. Hey, het core dumped. But it core dumped after deceiving almost finished. It's not too bad, but it's definitely, this is definitely the one that takes the most time, right? Although that is annoying as well. If only we could speed that one up. Yeah, I'm going to cook dinner. Wasn't working anyway, right? This is wrong. Very annoying. I want to measure the last part as well. Which I didn't optimize yet. See, unbelievable. Unbelievable. 0.8 seconds for row 0. Half a second for the next 33,300 rows. What? Okay, that's of course because this is not needed. That's exactly, the whole row is exactly all primes you need till the square root of whatever number we had, this number. So this is just a lookup. This is just finding all bits that are set and then calculate the prime numbers and adding them to the vector. Sorry, this one. No fancy calculations. I think it's basically addition, testing bits, shift, and a multiplication, and then storing it. Okay. Hey, looks it. I was about to leave because I'm going to eat. Well, I might scrape off a tiny little bit from this one, which was not optimized yet. But nah. I'll have a look at it. But this is definitely the big CPU eater, and I'm not sure how I can change, how I can improve that without changing the memory map of the whole sieve. So make it more cache friendly. Maybe I'm getting at my limits of being interested in this. It was all for fun, only for fun anyway. I like it when they make something that's perfect. So then if it would continue with this until it was perfect, which I'm starting to feel that I won't do, then it's something that you can just use the rest of your life. You know, it's just finished, cannot be improved. So whenever I would need prime numbers, after that point, I just say, oh, I have that code. Can't be faster, can't be better. The most optimal, best way to generate prime numbers. No brainer to use it over and over. So that's the benefit of continuing until something is really not just finished, but like you have the feeling that no, it cannot be better. This is just the perfect code. And I have code like that a lot actually. So I just keep using that. Stopwatch being one of them. I put a lot of time into that. If I want to measure something, I use my stopwatch. And I get like a single clock cycle precision. I mean, what more do you want? Okay, time to